Now we will discuss the estimation of thermal conductivity of molecular oxygen at 200 Kelvin and low pressure. This is the table 9.1 of 2 thermal conductivities, heat capacities and respective properties of gases at 1 atmospheric pressure, or we can even say it as low pressure. Now for the following question we need to obtain the values for oxygen at 200 Kelvin temperature. So the experimental values that are obtained for the given pressure of thermal conductivity is given here, that is 0.01833 watt per meter Kelvin. Then the respective heat capacity in joule per kg Kelvin is 911 joules per kg Kelvin, and the respective Prandtl number is 0.734. So we will use these values whichever is required in the given question. Now we will discuss the solution for the given question. We will first analyze the given conditions, that is low pressure, consider it as 1 atmosphere, and temperature at 200 Kelvin. Now using table E.1 from BSL book, obtaining the values of Lennard-Jones parameters, which are sigma is 3.433 angstrom and epsilon by kappa value is 113 Kelvin, and molecular weight of oxygen is 32 gram per mole. Now again using the table 9.12, we can obtain the molar heat capacity at 200 Kelvin for the oxygen, that is 911 joule per kg Kelvin, which can be converted to CGS units as 6.95 calorie per gram mole. Now at 200 Kelvin we can convert the Lennard-Jones parameters into kappa into temperature upon epsilon, which gives the value 1.7699. Now using the table E.2 and value of 1.7699 and applying little bit of interpolation, we can get the values of collision integral sigma, that is 1.228. Now using these values into the Chapman-Enskog equation for viscosity, that is mu is 2.6693 into 10 raised to power minus 5 into under root of molecular mass into temperature divided by molecular diameter squared into collision integral. And putting the values given, we can obtain the value of viscosity for the molecular oxygen at given conditions as 1.4755 into 10 raised to power minus 4 gram per centimeter second. Now to obtain the thermal conductivity from this obtained value of viscosity for molecular oxygen, we are going to use the Eugen approximation, which is given by the equation K is equals to Cp plus 5 by 4th time of universal gas constant into viscosity divided by molecular mass. Now putting the values into this question, the Cp value indicates the molar heat capacity which we calculated above, that is 6.95 calorie per gram mole Kelvin. So putting these equations values into the equations, we get the value of K, that is 4.3455 into 10 raised to power minus 5 calorie per centimeter second Kelvin. Now converting these dimensions into SI units, we get K is equals to 0.01738 watt per meter Kelvin. Now again utilizing the table 9.12, we can see that the experimental value given in the table is 0.1833 watt per meter Kelvin. So we can see that the calculated value for K, that is theoretical value that we have obtained from the Chapman-Enskog equation and using the Eucken approximation, the value of thermal conductivity is almost close to the experimental thermal conductivity value. Now we will discuss the following question. Predict the thermal conductivity of the following gaseous mixture at 1 atmosphere pressure and 293 Kelvin temperature from the given data on the pure components at the same pressure and temperature. Now, the species or the gaseous components that are included in the gaseous mixture is CO2, carbon dioxide, O2, oxygen, and N2, nitrogen. The alpha value indicates the main component of which the mole fraction is given by X alpha, the molar mass of the component given as M alpha, the viscosity of the component at given pressure and temperature, that is mu alpha, which is the value raised by 10 to the power 7, and the value of the thermal conductivity as K alpha, which is also raised as 10 to the power 7. Now we will look at the solution for the given question. For the following question, the given mixture, the thermal conductivity can be estimated using the semi-empirical equations as given by K mixture is summation of X alpha into K alpha whole upon summation of X beta into phi of alpha beta, where phi of alpha beta is the semi-empirical equation given in the form of 1 upon root 8 multiplied by 1 plus m alpha by m beta whole power to the negative of 0.5 into bracket of 1 plus k alpha by k beta whole power to 0.5 into m beta by m alpha whole power to 0.25 and the whole bracket raised to the power of 2. Now, so the value to be obtained for the given parameters will form a table with the following lists, where alpha value is mentioned, beta value is mentioned, the ratio of m alpha by m beta is mentioned, the ratio of k alpha by k beta is mentioned, the phi AB value is calculated, and the summation of x beta and into phi alpha beta is calculated. So the following table can be calculated using the calculator or putting the values into Excel file. Here the m alpha by m beta is the ratio of the molecular weight, where considering alpha as 1 is the carbon dioxide. So when alpha is equals to 1, consider carbon dioxide, and when beta is equals to 1, as in here, beta is equals to 1 also indicates carbon dioxide. So given mixture is assumed to be carbon dioxide, carbon dioxide. So the m alpha by m beta ratio will be 1, as carbon dioxide mass upon carbon dioxide mass will give the value 1. Similar is the case for k alpha upon k beta value, and same goes for the phi alpha beta value. Now in case of beta is 2, which is 2 is for oxygen, that is carbon dioxide and oxygen, then the m alpha by m beta value changes to 1.375. Also the corresponding K alpha by K beta value changes to 0.626, and thus putting those values into the above phi alpha beta equation, we get phi alpha beta as 0.687. And similarly, we can calculate this data for all of the conditions and all of the alpha and beta corresponding values. Now, upon obtaining all the phi alpha beta values, we may sum the following digits, that is for the alpha 1, for alpha 2 and for alpha 3. Now upon summing for the values, in case we get the summation of x beta into phi alpha beta as 0.686 for alpha 1, 1.005 for alpha 2 and 1.088 for alpha 3. Now, upon using the empirical formula shown before, we can use here the values x alpha into k alpha upon summation beta of x beta into phi alpha beta. So the k mix can be calculated by inputting the values used above, and thus the k mixture value for the given gaseous mixture can be obtained as k mixture is equals to 575.1698 into 10 raised to power minus 7 calories per centimeter second Kelvin. Thus, the thermal conductivity for the following gaseous mixture at 1 atmosphere and 293 Kelvin temperature is obtained from the given data set. Now we will discuss this question. Estimate the thermal conductivity of ethane at 183 degree Fahrenheit and 197.9 atmospheric pressure from the experimental value of thermal conductivity K is equals to 0.0159 BTU per R feet at 1 atmosphere and 153 degree Fahrenheit. Plot for the reduced temperature versus reduced thermal conductivity that we will refer for solving the questions requiring the values of the reduced temperature and reduced pressure conditions. For example, in this question we have to obtain that TR is 1.116 and the respective PR is 0.2021. Then the point lies somewhere between here. Now in the same question we can also see that for TR is 1.17, the PR value is 4.16. Then we will see this curved line for the PR, and respectively we will calculate the KR point by plotting the points, that is PR is 4.16, so it will be somewhere here, and respective value of TR will be this line like this. Then the KR value we are getting is somewhere here like this. So this will be the value that we are getting, and this is approximate 2.35 or 2.3, or we can even assume it as 2.4 due to considering some of the errors that may be there. Thus we are using the plot that is given in the BSL book to calculate the critical points or the reduced values for the given conditions. Now we will discuss the solution for the given question. Here the estimation of thermal conductivity can be done by utilizing the temperature and pressure dependency of thermal conductivity. That is the plot that is given between the reduced temperature and reduced pressure, that is figure 9.2 of 1 in the BSL book. First, we will determine the reduced temperature and pressure quantities for the given condition. The reduced temperature can be given as the T, that is the given temperature condition, upon Tc, that is the critical temperature condition, and the reduced pressure can be given as P, which is the given pressure condition, upon P critical, which is the critical pressure condition. Now, by using the table E1, we can obtain the Tc, that is critical temperature condition, and Pc, that is critical pressure condition for ethane gas. So the Tr can be calculated as the equation, and PR can be calculated using the given relation. Now we have to keep in mind that the temperature given in the question is in Fahrenheit, so we will have to convert it into Kelvin for be abiding to the relation that is given in the reduced temperature and reduced thermal conductivity relation, that is in the plot. So upon calculating the TR and PR values, we will now utilize the figure 9.21 and obtain the values of PR and TR, that is the reduced pressure and reduced temperature conditions. Now, as we look into the plot for the value of reduced thermal conductivity, we obtain the value of Kr, that is the reduced thermal conductivity, as 0.36. Now, Kc, that is the critical value of thermal conductivity, is given as K, thermal conductivity calculated upon reduced thermal conductivity. So we obtain the value of critical thermal conductivity as 0.0442 British thermal units per hour feet Fahrenheit. Now, at the given conditions, that is 183 degree Fahrenheit and 197.9 atmospheric pressure, we need to calculate the reduced temperature and pressure, which can be find or calculated using the above relation. T by Tc and Tr is equals to P by Pc. So as we have calculated the temperature and pressure reduced conditions, again we will use the table or figure 9.21 and obtain the value of reduced thermal conductivity. Now once we have obtained the reduced thermal conductivity, that is Kr 2.4, then we can apply the relation Kr is equals to K by Kc. So K is equals to Kc into Kr. Here K, or thermal conductivity that needs to be found at the given condition, is given as 0.0442 into 2.4, which results in 0.10608 British thermal unit per hour feet Fahrenheit. Now, at this condition, the experimental value of thermal conductivity found is 0.048 British thermal units per hour Fahrenheit, which is largely deviating from what K value we have obtained above theoretically. Now, this indicates the deviation in the properties for polyatomic molecules, as the relation we are assuming above is considered for the monoatomic molecule. Now, ethane, that is C2H6, is not a monoatomic molecule in reality. So, this deviation occurs especially in case even if it's considered near the critical point of the molecule, or the condition is far from the critical point of the molecule. Thus, this is the deviation we can see, and hence this correlation cannot be relied on for solving the temperature or pressure conditions and obtaining the thermal conductivity of the molecule.